Hi guys, this is your very first lesson in BC Calculus. This is going to be an introduction to limits. Now our objective for today is just to give you guys a working definition for the limit of a function. We are going to go into the precise formal definition of a limit in the next lesson, section 1.2. But for section 1.1, we're just going to actually calculate and find limits of functions. So let's first explore the concept of a limit of a function by first answering some questions about the graph of g of x, which is a piecewise defined function here. Okay, let's begin with our first example. Let's evaluate g of 4. So in other words, I want to evaluate our function g at x equals 4. So I'm going to go to x equals 4, and it looks like at x equals 4, the y output, g of x, is 3. So we get g of 4 is equal to 3. Now, to evaluate g of 0, we need to look at x equals 0. Here we have two different points. One is a closed circle at 0, 1, and one is an open circle at 0, 3. We want to choose the one that is the closed circle. That's what g of 0 is defined as. So g of 0 is 1. G of 2, same issue. When we look at x equals 2, we have two distinct points. Please make sure you're always going with that closed circle. So g of 2 is equal to 5. It is not equal to 0. I've seen some students do that mistakenly with those open circles. They get a little confused. Now question 2 is posing a much different question. We're not evaluating our function. Now we're asked, as x gets close to 0 from the left, what does g of x approach? So let's make sure we break down this into two parts. As x gets close to 0 from the left means you're going to approach x equals 0 from the left. You're going to continue to look at values closer and closer to x equals 0. And you want to know what your output, the y values, approach. So you want to know what g of x approaches. In other words, you want to know what your y values approach. Not what they're equal to, but what they approach. So if we answer this question, okay, we're going to be on portion of the function here that gets closer and closer to x equals 0 from the left of 0. Now as you can see, as x gets closer and closer to 0, our function, the graph here, gets closer and closer to a y output of 1. So g of x, or y, approaches 1. Now question 3 is really similar. However, this time we're going to get closer to 0 from the right. So we want to look at x inputs that get closer and closer to 0 from the right hand side. So we're going to follow that function here and get closer and closer to values of x equaling 0. Notice that the y outputs get closer and closer to a value 3. Notice g of 0 is not equal to 3, so we're not really evaluating our function. We're just finding what values our function approaches. Now, example 4 asks, as x gets close to 4 from the left, what does g of x approach? So I'm looking at x equals 4. I'm approaching it from the left. As I get closer and closer to 4, my y values get closer and closer to 3. It just so happens it's the same answer as the last one. They're not really related to each other. Okay, now number 5 asks, this time, again, same question, but posed from the right. So we want to come from the right. Now our function, as the x values get closer and closer to 4 from the right, also approaches the same exact value, 3. Now question number 6 asks, as x gets closer to negative 2 from the left, what value of y does your function approach? So in this case, if I actually let x equal negative 2, I do see a vertical asymptote there, which means negative 2 is not in the domain of the function because g of negative 2 does not exist, right? But who cares about that? We don't really care what happens at negative 2. We just want to know when x approaches negative 2 from the left, what happens to that y value. So as you can see, if we follow our function and we get super close to negative 2, so we start getting x values that are really, really close to negative 2, we start getting y values that are huge. They're really very large, but they're negative values. So really large negative values, meaning they're going towards negative infinity. They are unbounded. They continue to get larger and larger negative values. So our function approaches negative infinity from the left-hand side of negative 2. Now from the right-hand side, question 7, asks from the right-hand side, what does your function approach? So from the right, our function, as we get closer and closer and closer to x equals negative 2, but we never quite hit it. As we get closer and closer and closer, we see that our values are again unbounded, but this time in the positive direction. So we have positive infinity for the value that g of x approaches. Again, sorry, I shouldn't say value because infinity is not a number, it's not a value, but our function does approach positive infinity. Okay, so later in the lesson, we are going to come back to this warm-up question that we started with. This is just kind of getting you transitioning into the idea of thinking about limits of a function. So we're going to move on now and talk about our working definition for the limit of a function. So we began with those intro problems because I think it really helps you to understand the difference between evaluating a function with a given input, okay, versus looking at the values that your function gets closer to as you get closer to a specific input. Now, in calculus and its applications, we're often interested in function values. So let me highlight this. We're often interested in function values f of x. In other words, we're looking at the y outputs of some function f when x is close to a number a, but not necessarily equal to a. That's very important. We don't necessarily care what happens when x equals a, but we want to know what happens to f of x, what those y outputs look like when x gets really close to that number a. Now we're going to take a look at a function f of x equaling x cubed minus 2x squared over 3x minus 6. So this is a rational function with an a value of 2. Now note that 2 is not in the domain of this particular function, because if you try to evaluate f of 2, you end up with 0 divided by 0, so it's undefined, which means that f of x is not defined if x is equal to 2. So we have to throw that out of the domain. Now there is a table of values here that I want you to take a look at. Okay, what we have are values of x and values of f of x. Notice these values of x get closer and closer to 2, but they don't actually equal 2, again, because, one, they're undefined, but we don't care about when they're equal to 2. We just want to know what happens to the y values as x approaches 2. So here we're approaching 2 from the left. Here we're approaching 2 from the right. Now those y values here look like they're approaching a number. I already know what that number is, but it's kind of hard to see with these decimals what that number might be approaching, that y value, until you get even closer increments. So here I'm super close to x equals 2, right? From the left and from the right, getting closer. And as you can see now, those values here get closer and closer to a specific value. If we continue to get smaller and smaller increments away from x. So we're really super close to 2 now. We can see that those values here, those y values, look like they're going to the same value, 1.3333 repeating. That's 4/3, okay? Okay, now let's answer a couple of questions here pertaining to our function and our a value. Now, as x got closer to a, so as x got closer to 2, and we plugged in those values into our function, did our outputs, those function values f of x, did they get closer to some real number L? Well, we said yeah, they did. And if somebody wasn't convinced that they were getting closer to 4/3, you can always, plug in a value that's even closer to L to see if that value here, that output, gets closer to 4/3. So in this case, yes, right? L was equal to 4/3. Now, question 2 asks, can we make the function value f of x, so can we make our y output as close to L, so as close to 4/3 as we want, by choosing an x value that is sufficiently close to a, but x not equaling a? Now, question 2 might be worded in a way that is a little confusing, but all that it's saying is that, can we make our function value f of x, so that y output, closer and closer to L, by choosing values of x that are closer and closer to a? Absolutely. That's what we just saw in our table. We can continue to try to input values of x that are even closer to a, which is 2, and then get outputs that are closer and closer to 4/3. So the answer here is yes. Now, if we answer both of these questions with a yes, we will use this notation here. This is the limit notation. Out loud, we would say the limit of f of x as x approaches a is L. So we can also see that, or read that as f of x approaches L as x approaches a. Okay. Now, in our example, that notation would be written like this. So our a value was 2. So the limit of f of x, so the limit of x cubed minus 2x squared over 3x minus 6 as x approaches 2 is 4/3. Okay, so that is the definition, our working definition, that we're going to use now throughout this lesson. In the next lesson, we will learn a more precise formal definition for the limit of a function, but for today, we're just going to kind of work through some examples using this definition here. Now, you don't have to necessarily rely on a table of values to find the limit of a function. In this particular case, I'm going to show you a different way, an alternative method for finding the limit. You can solve algebraically, and then we can even graph our function as well. So let's say I wanted to graph this particular function. Now, I'm going to factor out the x squared here in the numerator. So I have x squared times x minus 2. And I'll factor out a 3 in the denominator. And then I end up with common factors of x minus 2. So after I cancel them, this rational function is really a quadratic function. Okay, this simplifies to a quadratic function. Now this quadratic function is centered at 0, 0, but it does have a hole. Now that hole occurs because x equals 2 is not in the domain of this function. Remember, if you plug in x equals 2 into your original rational function, you end up with 0 over 0. I'm sorry, f of 2. Okay, so it's not in the domain of your function. So if I plug in 2 into the new function here, I see that I end up with 4/3. So at, let's do, I don't know, 2 comma 4/3, we have a hole in our function. So graphically, we can even see as x approaches 2 from the left, the y values approach, the y approaches a value of 4/3. As x approaches 2 from the left, or from the right, geez, I can't even think right now. As x approaches 2 from the right, your y approaches a value of 4/3 as well. So it doesn't matter that your function doesn't exist at 2, right? We don't care what happens exactly at 2. We only care about the fact that as it approaches 2 from the left and from the right, your function approaches 4/3. Okay, I know I've already said this a little bit, but I really want to stress it. Now, a major idea for you to wrap your head around is that when you find a limit of a function, we want to know what happens to our function as x comes close to approaching a certain value a, but we don't actually care what happens when our function equals a. We only care about what happens immediately around a. So as it gets really, really close to a, we want to know what happens to the function, but not when it equals a. So here I've got three different examples of functions in their graphs. So we have three different functions here, and each of the graphs is pretty similar, but they're not exactly the same. The reason why I'm showing you these three graphs and these three functions is that each one of them looks different. However, they all have the exact same limit. Okay? The limit of each of these functions as x approaches 1 is the exact same. And that's because, again, we don't care what happens at the actual value x equals 1. We only care about what happens right around it. So in our first function, this linear function here, as x approaches 1 from the left and as x approaches 1 from the right, we end up with a limit of 8 because that y output approaches 8. Okay? Now in the graph over here of this rational function g of x, after we, it looks a lot different than the linear function, but after you factor out the numerator here and you realize you can cancel those like factors, you end up with that linear function, except for now it has a hole at 1 comma 8, right? If you plug 1 back in your function, you end up with 1 comma 8, so that's why we have a hole here. But we still only care about what happens as x approaches 1. So as x approaches 1 from the left and as x approaches 1 from the right, that limit here is 8 because our y value, right, that f of x output approaches 8 as well. It doesn't matter that there's a hole, it still is approaching the value 8. Okay, and finally we have the graph of h of x here, which is a piecewise function. Now, it's defined with that same rational function for all values of x except for x equaling 1. So we do have a linear function here with a hole at 1, 8, the same exact graph as g of x. However, we define at x equals 1, 1 comma 4. So here we have that point 1 comma 4. So we see, you know, a different thing going on at the value x equals 1, but it doesn't matter because we're concerned about what happens when x approaches from the left. So as x approaches 1 from the left and as x approaches 1 from the right, what happens to our y output. And again, in this case, who cares about that coordinate here? It's still approaching the value 8. So that's why our limit here is 8. So please make sure you understand that despite what the graph looks like, you know, they could have some kind of weird thing going on at the specific value that your limit is approaching. But it doesn't matter. You don't care about what happens right here at x equals 1. You care about what is happening right around it. Alright, let's head back now to the original example on the front of our notes. Given the graph of this piecewise function, I want to evaluate some limits. Now, the notation is a little bit different in this very first example. We're finding the limit of g of x as x approaches 0, but this time now it has that plus sign here on the right. What that plus sign is denoting is that you're going to approach 0 from the right-hand side. Okay, from the right of 0. So from our function here, if we take a look, at the graph of our function, we can see that as x gets closer to 0, y gets closer and closer to 3. So the limit of g of x as x approaches 0 from the right is 3. Now the next example here, the limit of g of x as x approaches 0, this time we want to know as we approach 0 from the left of 0. So as x approaches 0 from the left of 0, we can see that those y values approach 1. So the limit of g of x as x approaches 0 from the left is equal to 1. Now our third example asks us again to find the limit of our function as x approaches 0, but without specifying if it's from the left or from the right-hand side. So let's think back to our working definition for the limit of a function. As x is approaching 0, so as x gets closer and closer and closer to 0, do we see our function getting closer and closer and closer to some y value? In this case, we have to say no, because as you can see from the graph, we're not getting closer as we get closer to 0. We're not getting closer to a single y value. Here we see two different ones. So the limit of g of x as x approaches 0 here does not exist. And that now brings us to the theorem below here that says that the limit of f of x as x approaches a exists if and only if both your right hand and left hand limits exist and they are equal to some real number L. So the notation that you can see here, the limit of your function as x approaches a exists if and only if the limit from the left and from the right is the same. So let's keep that in mind as we answer some additional examples here. The next example asks us to find the limit of our function as x approaches 2 from the right. So from our graph here, as we get closer to 2, so as our x values get closer to 2, our y values approach 0. So we want to say here that the limit of g of x as x approaches 2 from the right is 0. Now I know some of you might be thinking, well, at x equals 2 though, we have a y output of 5. That's this coordinate here. And you're right. We don't care though what happens when x equals 2. We just want to know as x gets closer to 2 what happens to our y values. And that y value gets closer to 0. Now from the left hand side, which is what this next question is asking, we can see that as x gets closer to 2 from the left, our y approaches 0. So the limit here from the left of 2 is 0. So because our left and our right limits are the same, they are both 0, the limit as x approaches 2 of our function is 0. All right, now so far in this lesson, I've shown you two different methods to find the limit of a function. We started off with a table of values. When we looked at that rational function, we looked at values that approached 2. Now, we got really, really close to 2, and our y outputs got really, really close to 4/3. That's how we found that the limit was 4/3. That would take a long time though if every time we looked at a function we had to calculate, using a table. So we can also look at the graph of a function to see what happens as we approach certain values, like what we just did with our piecewise function. But let's say that you're not really comfortable graphing a certain function because you don't know what it looks like, and it might take you a really long time to figure out what that graph looks like. Or maybe you don't have a calculator with you, so you can't evaluate your function at very, very close values of x near a. In that case, what you're going to do is rely on another method, which is to find a limit algebraically. Okay, so we've already found the limit of this function here at x as x approaches 1, and we found the limit of this function here. Those are the graphs above. So let me go up to them. Here's the graphs right, whoops, just past them right here. We saw that the limit was 8 and 8 here. Now, if we come back to this algebraically, the first thing I want you to always do is plug in x equals a into the function. Okay, plug that in because that's the fastest way to find what that limit is going to be for your function. So if in this particular example, if I just plug in 1 into that function, I end up with 8, and that is the limit of x plus 7 as x approaches 1. So that's the first thing I always want you to try. Okay, now that's an easy problem, right, because we just get a value. Here, if we try to plug in 1 right away into that function, we get 0 over 0. So here we have to use an algebraic manipulation. Here we must factor the numerator, so we'd have x plus 7 times x minus 1 over x minus 1. And then once I cancel those common factors here, after now I'm looking at the limit as x approaches 1 of x plus 7, again I just plug in 1 here and I'm going to get 8. So the limit here is 8. So that's what it means to define a limit algebraically. You're going to plug in a value and evaluate your function actually at the value a. Now for example 3, we have to do some algebraic manipulations again, because if I plug in 1 here into that function, I get dividing by 0 one more time, so 0 over 0. So here I'm going to factor out that 2, so I have 2 times 1 minus x squared over x minus 1. Now this is going to factor in the numerator to 1 minus x times 1 plus x. And again, you need to be able to recognize this, that you've got opposites here, 1 minus x and x minus 1. So if I factor out a negative, now I have, whoops, in the numerator, whoops, x minus 1 times x plus 1 over x minus 1. So I'm going to cancel those like factors, and I have the function negative 2 times x plus 1 left over. So I'm evaluating, or I'm sorry, I'm looking at the limit as x approaches 1 of negative 2 times x plus 1. So here, again, I'm going to plug in x equals a. So we'll plug in 1 into the function here. So we have negative 2 times 1 plus 1, which is negative 4. So the limit of 2 minus 2x squared over x minus 1 as x approaches 1 is negative 4. Okay, let's try number 4 now. So again, if you're trying to find the limit of a function and you don't have a graph and you don't have a table of values already given to you, then you're going to try to find it algebraically. And the first thing you try algebraically is to always plug in this a value here, right? As x approaches a, that's a is equal to 9, we're going to plug in 9 into the function. Now if we do that, we end up with 9 minus 9 over root 9 minus 3, so 0 over 0. So that doesn't help us to find the limit here. Instead, we have to do some algebraic manipulations. So let me erase real quick. Let's try getting rid of that radical by multiplying by the conjugate here. So let's multiply by root x plus 3 over root x plus 3. Now by multiplying by that conjugate in the denominator, I've created a difference of squares. So if I square root x, I get x, and if I square 3, I get 9. So this is x minus 9 after I FOIL that out. In the numerator, I still have x minus 9 times root x plus 3. And as you can see, those common factors here will cancel, and I'm left with root x plus 3. So if I want to find the limit as x approaches 9 of root x plus 3, we're going to just evaluate the function at x equals 9. So I plug that in, and I have square root of 9 plus 3, which is 6. So the limit as x approaches 9 of x minus 9 over root x minus 3 is 6. Okay. Now there is an alternate way. Instead of multiplying by the conjugate, let me erase it once again. If we go back to that original function here, x minus 9 over root x minus 3, instead of multiplying by the conjugate, I'm going to try to factor the numerator. Okay, you might think, well, you can't factor x minus 9. However, I recognize, hey, root x minus 3, that multiplied by root x plus 3 would create a difference of squares. It would just be root x squared, which is x, minus 3 squared, which is 9. So I just factored x minus 9 into root x minus 3 times root x plus 3. So that root x minus 3 in the denominator will cancel the root x minus 3 in the numerator, leaving you with this function root x plus 3. So we're going to find the limit as x approaches 9 of root x plus 3. Okay, and if I evaluate again when a is equal to 9, I have root 9 plus 3, which is 6. So again, I'm not going to rewrite it, but you can see that the limit as x approaches 9 of x minus 9 over root x minus 3 is going to be 6, no matter which method you choose here. Okay, the last portion of this lesson is a pretty important one. It's going to weave two different concepts together. Now sometimes when you are given a function and asked to find the limit of that function as x approaches a certain value, you're not able to use any algebraic manipulations to find the limit. So sometimes functions are given where you cannot use algebraic manipulations to find a limit. So in those cases, you're going to have to rely on graphing your function or constructing a table of values, the other two methods like we talked about before. Now it may also be the case that when you're asked to find the limit of a function as x approaches a certain value of a, you might see that the limit does not exist at all. In some cases, the limit doesn't exist, like we saw in that piecewise function. They didn't exist because you had two different values from the left and from the right of 0 that you were approaching. So in that case, obviously the limit doesn't exist because we're not going to a single value of y. Now there's other cases though where the limit doesn't exist, and that's what we're going to specifically look at. These three cases occur when you have a vertical asymptote in the graph of your function. Whoops. Now, when a function tends towards its asymptote, so let me draw in an asymptote here. It's got a couple different options, right? Like, let's say it's coming from the left. From the left, it can go up or it can come down. It can go towards positive infinity or towards negative infinity as it gets closer and closer and closer to that vertical asymptote. From the right-hand side, the same thing. It can tend towards positive infinity or from negative infinity. Now, because of those options here, we really have three distinct cases. Okay, so case one is when from both sides of your asymptote, your function tends towards positive infinity. Okay, now case two is when, as you approach that asymptote, your function behaves in different ways. From one side, it'll go towards positive infinity, and from the other to negative infinity. It doesn't matter if it's on the other side, like if it approached from the right and went up, and from the left it went down. Doesn't matter, it's just two different directions, okay? Third case is if your function, as it approaches the vertical asymptote, tends towards negative infinity. So from both sides, we have values that get unbounded in the negative direction. Now I want to stress that in each of these cases here, if we were asked to find the limit of the function that is depicted here in graph number 1, we would say that the limit does not exist because we're heading towards positive infinity, and positive infinity is not an actual value. Those values continue to get larger and larger. They never approach a single value because they just get bigger and bigger and bigger. So the limit here does not exist, and the same goes for pictures 2 and 3. The limit really doesn't exist. However, we want you to specify when you're asked to find the limit of a function as x approaches a, and a happens to be a value for which you end up with a vertical asymptote. We want you to specify what happens to that function as it approaches the vertical asymptote. So for case 1, you would say that the limit approaches positive infinity. For case 3, obviously here you would say that the limit approaches negative infinity. Now for case 2, because your limit here, because your function here is tending from either side of your asymptote, it's tending in different directions, your limit just does not exist. Okay, so we specify a little bit further, we just say it does not exist. All right. So we're going to look at 2 examples where we bring both of these ideas together. We can't use algebraic manipulations to find the limit, and in fact when we try to find the limit does not exist because we have a vertical asymptote. So let's take a look first at example 1. Okay, so we want to find the limit as x approaches 3 of this rational function 2x over x minus 3. Now the first thing I always want you to do when you're asked to find a limit is plug in that a value into your function. Okay, now here if we do that, we end up with 6 divided by 0. So we have a constant 6 divided by 0. Now if you end up with 0 divided by 0, that always gives you a hole in the graph of your function. But here, if we have a constant over 0, instead of giving you a hole, because you can't factor here anything else, no algebraic manipulations can be done here to that function, this time we are going to get a vertical asymptote at x equals 3. Okay, so our function is undefined when x is equal to 3. So we have that vertical asymptote here. So 0 divided by 0, you're going to get a hole in the function, but a constant other than 0 divided by 0, this is where your function has a vertical asymptote. And as we discussed, whenever you have a vertical asymptote, your values have to tend towards 3 different cases. So we do not have an actual limit here, so the limit does not exist. Okay, so I want you to state that first. Limit does not exist, but then we're going to decide between the 3 cases. Are our function values heading towards positive infinity, negative infinity, or are they going in opposite directions, which means the limit just does not exist? All right, so let's figure that out. So what we will do is analyze our function and the graph of our function as our x values approach 3 from the left and 3 from the right. Okay, so we want to get really, really close to x equals 3 from the left and from the right. So if we wanted to get x close to x equals 3 from the left, that means we would want to be inputting something like 2.999999999, something crazy, close to 3 from the left. We would want to plug that into our function. Now, if we plug something like that into our function, we get something. It's 6 point something, obviously, but let's say it's very close to 6. Divided by a number that is negative now, but very close to 0. Okay, so if I inputted 2.9999999 into that function, I'm going to get a number that is negative, but very close to 0 still. Now, when I take 6 and I divide it by 0, that number blows up, right? That's it's infinitely large, but it's infinitely large in the negative direction. So as x approaches 3 from the left, my function is approaching negative infinity, okay? Now, as x approaches 3 from the right, if I plug in a value like 3.00000000000000001, then this time when I plug it into that function, the numerator is still very close to 6. The denominator, though, is positive, okay, and close to 0. So when I look at this value here, this is heading towards positive infinity, like so. So the graph of the function as it approaches the vertical asymptote x equals 3, those values tend towards different directions. So we would say that the limit just does not exist. So here's how I'll write my final answer. The limit as x approaches 3 of our rational function 2x over x minus 3 does not exist. Okay? All right, now let's look at number 2, which is very similar to number 1. We have 2x over x minus 3 squared, and we're approaching x equals 3. So in this case, if we right away start with plugging in 3 into the function here, we have 6 divided by, again, 0, because 0 squared is still 0. So in this case, we have a vertical asymptote, okay, and again, it'll happen at x equals 3. Now, we know the limit does not exist, but we want to specify which one of those 3 cases occurs. So what we'll do is we'll analyze what happens as x approaches 3 from the left and what happens as x approaches 3 from the right. Now this time when we input a value that's really close to 3 from the left, something like, 2.99999, when you plug that in, we would get a negative value on the inside of the parentheses, but then it'll be squared. So it'll always be positive in the denominator. So we have, whenever we plug in something to the left of 3, but really close to 3, we'll have a number that's close to 6 divided by a number that's close to 0, but positive. So in this case, as x approaches 3 from the left, you can see that those values will tend towards positive infinity. And from the right, if we plug in a value that's very close to 3, on the right-hand side of 3, that'll be a number like 3.0000001. If you plug it into here, you have a positive squared, so of course that'll stay positive. The numerator is also positive as well, so you'll have a number that's close to 6, okay, divided by a number that's close to positive 0. So here we can see that on both sides of that asymptote, our values tend towards, our y outputs here tend towards positive infinity. So for our answer here, the limit as x approaches 3 of 2x over x minus 3 squared, it does not exist, but it tends towards positive infinity. So that's how we're going to write that up, okay? All right, thank you so much for sticking in there to the end. I know this is another long lesson, but I really appreciate it. Hopefully you'll have a very good foundation with the start of calculus, okay? Tomorrow we'll work on the precise formal definition of finding a limit. Nice job. See you tomorrow.